we'll continue with module 2. Okay. Yep. Okay. Okay. So this is where we left off last week. Oh, sorry, actually on Monday. So we, oops, okay. So we basically combine the equations, we solve, well, we integrate, we solve, and then we get this final expression for the number of electrons, right? But actually, I can use another expression, okay? And I actually can start introducing this term. If you remember, our Fermi energy, we calculated it before in, if you remember the previous slides, it's basically in the middle of the energy gap, right? So that's why we can replace, so we can basically, yeah, so we can basically replace the Fermi energy with the value of the Fermi energy in an intrinsic semiconductor, that is the band, the half of the band gap energy, right? And then we can also introduce this term, because this term, you see, it seems a bit new here. Actually, if you realize, if you compare this, right, you have mass, the mass of the electron to the 3 halves. Here you have m naught to the 3 halves over m naught divided by, sorry, me divided by m naught to the 3 halves, right? So I'm basically multiplying by, or sorry, dividing by the same term, so it doesn't affect. But the idea here is just to introduce this term, and this term, actually, the whole term right here, that is the effective mass ratio. So the ME that you see here with sort of a star there, that's actually the effective mass, and that is because in reality, the effective mass of an electron is not really the mass of an electron at rest. It's not really the mass of the electron that you know we all know, and you can Google it. It's not really that value, right? So in order to sort of yeah, we can say, to try to be more realistic, in quantum mechanics, you can introduce this term, right? And this term doesn't really break the law, because at the end you're still multiplying, because just realize you have m naught here to the 3 halves, and you're dividing by m naught to the 3 halves. So at the end, you're just multiplying by a term that is mass, like here, a term that is mass to the 3 halves, right? So you're not really modifying a lot, you're just making this more realistic, and the idea is, or making it more realistic, introducing this whole term right here, that is the effective mass ratio, right? I'm just dividing the effective mass of the electron by the mass of the electron at rest, right? The mass of the electron that we all know. And that is actually all of this term, this big term right here, that can be defined as a constant, right? And so that constant equals this value, 4 times 84 times 10 to the 15. And then you get the whole expression, or this expression, that that is actually dependent, right? So the mass of the effective mass, it has its value, and then obviously it depends on temperature and on the value of the energy gap. Okay, is that clear so far, guys? So you can definitely see that the number of the electrons in the conduction band is a function of temperature and is a function of the energy gap, as we expected, right? And you can see, actually, there is an exponential term right there, and that is quite interesting, right? You do have this term, but this term is actually not as big as this term. Let me use another color. This term here that actually has a bigger influence on the value of the number of electrons in the conduction band, right? Just because it's an exponential term. So actually, you can if you were to calculate this for silicon, for example, you will get about a number of about 10 to the 9 electrons per cubic centimeter, right? If you were to calculate it for silicon at room temperature. So if you see at room temperature, 10 to the 9 electrons in the conduction band is quite a small number. If you're a conductor, you should have at least on the order of magnitude of 10 to the 24 or even bigger number of electrons. So imagine 10 to the 9 is quite a small number, and that is why silicon at room temperature, pure silicon, is a very poor conductor. It's basically a semiconductor because it only has, if you apply this equation and solve for silicon, you will get only 10 to the 9 electrons per cubic centimeter in the conduction band. Okay. Now, if you look at the graph at the bottom, you can see that what is plotted there is the functions, right? You have there, well, you have here the population density versus the energy, and then you have the function, right? The Fermi distribution function. If you see the area that is sort of gray, the gray area that you have there, that's actually the density of electrons, and because remember, if remember that that in semiconductors, there is not only electrons contributing to conduction. There are also holes, because remember, if an electron jumps to the conduction band, then it leaves a hole in the valence band, and that hole also contributes to conduction. Therefore, you can see there the area of the density, or the area that is enclosed there by the Fermi distribution function, the area that is enclosed, and by the exponential term here, right? By the exponential term, you will get, or you see that that area actually belongs to the density of electrons, and obviously if we're in the valence band, also corresponds to the density of holes, okay? So it's basically the area that is enclosed by the Fermi distribution function and by the population density, okay? And if we're talking about intrinsic semiconductors, it has to be the case that the number of electrons must be equal to the numbers of holes, right? So the number of electrons that have jumped to the conduction band, it must be equal to the numbers of holes that are left behind in the valence band. Therefore, I can actually say, or I can actually write an equation for this, for the population density of electrons. I can write an identical equation for the population density of holes, right? And it will be the same. It must be the same number. Okay. Now, so what else contributes to conduction, right? Because we're saying, okay, it basically depends on electrons and holes. But it's not just that. It's actually the mobility, a key factor here. The mobility of the, in this case, of electrons and holes. So the mobility in general of any current carrier, right? And the mobility is defined as the velocity per unit electric field. So in general, and this will be the key equation, right? The conductivity of or in a semiconductor, and in general, we'll see that this doesn't only apply to semiconductors, equals the population density, or the number of electrons and holes, right, in this case. So that's N, times the mobility, that's mu, and times the charge, right? So if you expand actually that equation, I'm just combining this equation and you will get this equation, right? That's just combining equations. If you look back at the equations in the first module, you might remember those. Okay, so if I expand this equation, I can actually sort of break and separate this equation into two terms and define one for electrons. So that will be the number of electrons in the conduction band, the charge of the electron, and the mobility of the electrons, plus the number of holes in the valence band, times the charge, that basically will be the same but with opposite value, and the mobility of the electrons, right? So I can replace, so I can use this term because I already have an equation for this value. I already have an equation for that. So I can replace that value, right? And I can use, so it will be the constant times the charge and times the mobility of both, right? And times the exponential term. So it's just, this is just literally replacing n of v and n of h with, because remember, that must be the same. So you just replace for them and it will be, you will get this equation, okay? And this is actually the equation that defines conductivity and that allows me to calculate the conductivity of an intrinsic semiconductor. Is it clear, guys? Okay. Okay. Now, so if you look at the equation, right? It depends on two factors, right? The number of electrons, or the number of current carriers, it might be electrons, holes, and the mobility of them, right? So there are two factors. But if you think about these two factors, they are actually competing. Why? If you increase the temperature, obviously the mobility of those current carriers will be reduced. You tell me why? They are moving more. Electrons, if I increase temperature, electrons move more. Yes, but the fact that everything, not only electrons, start to move, it means that there will be more scattering. So to say, there will be more collisions of electrons with phonons, more collisions of electrons with other electrons, and therefore their mobility, the actual value of mobility, so mu, actually gets reduced. Because again, more temperature, everything is more mobile. So there will be more scattering, more collisions of electrons with phonons, of electrons with other electrons, and therefore mobility reduces. On the other hand, though, if I increase the temperature to, let's say, room temperature or even higher, I'm actually giving more energy for electrons, more energy, that obviously more thermal energy, and that energy gets basically is taken advantage by the electrons in the valence band, so they can jump, or so they can get enough energy to jump to the conduction band. Therefore, I'm actually, if I increase the temperature, I have these two competing effects. I'm reducing the mobility, right? So this term is becoming smaller, but I'm also increasing the number because I'm giving more energy, so more electrons are capable of jumping into the conduction band. So I'm increasing this number. So what happens overall with conductivity? Well, actually, the first term dominates. So N dominates. Therefore, and look at this, mobility and temperature, right? So mobility decreases with increasing temperature. Okay, yes, makes sense. Number of current carriers increases with increasing temperature. But if you combine both, actually, the increase in number of current carriers is more significant, and therefore you see overall conductivity actually in semiconductors, in intrinsic semiconductors, increases as I increase the temperature. Is this clear, guys? Okay. That's enough for intrinsic semiconductors. Time to jump into extrinsic semiconductors, okay? In general, or it's very rare to have intrinsic semiconductors, so pure semiconductors. Actually, we do things to semiconductors, and that thing that we usually do is called doping. So we basically introduce other atoms that can help me to carry more charge or to carry more current. So, and usually what we do in semiconductors is adding either elements of group 3 or of group 5, because remember, semiconductors like silicon, germanium are usually, or are in group 4, belong to group 4 in the periodic table. So I usually choose elements that are either in group 3 or group 5. And what do? Well, they go and replace some atoms in a substitutional manner. So let's consider the case of putting phosphorus, right? I just add, let's say, one small atom of phosphorus in my silicon lattice. Okay. Phosphorus has 5 valence electrons. So 4 of them will go and form the regular electron pair bond with the neighboring silicon atoms, because remember, silicon has 4 atoms in its valence shell, right? So it pairs, or 4 of those 5 valence electrons in phosphorus go and pair with the silicon electrons. But that 5th electron is loosely bound to silicon because it's not really forming a pair, because it doesn't have anything to pair with. So it is bound to silicon, but not strongly like the other 4 electrons, right? So if I increase the temperature slightly, that electron says, well, actually, I can run away from here. I can go somewhere else. So that electron dissociates from the lattice and starts traveling through the crystal. And that fact that an electron is traveling, we all know that is conduction, right? Obviously, for that, I need to apply a voltage, right? So this type of electrons, so if I'm putting a material that has more electrons, or that will give me an electron that will be able to fly free through the crystal, well, that is a donor electron. And therefore, these materials are called N-type semiconductors, because I'm adding a negative charge. That's why it's called N-type, because I'm adding one more negative charge. And obviously, these are the electrons that will be able to jump, or that is easier for them to jump from the valence band to the conduction band, and therefore they will populate the conduction band. Okay, so I think you guys knew this. This is quite easy, I believe. Okay, and I can do the same actually for elements that are in group 3. In that case, they will have 1 electron less than silicon. And that means I'm introducing, or you can say you're introducing a positive charge, because you're leaving one of those electrons in silicon that should or is supposed to be bound. Now, because I'm introducing an element that only has valence 3, therefore one of those electrons from silicon will be free, and now that can basically travel around the crystal. So I'm introducing a positive charge. It's not really that I'm introducing a positive charge, but you can consider that. So in that case, you are adding acceptor impurities, right? And actually that creates holes, or what's called positive carriers, right? Therefore, we call these conductors p-type or positive type semiconductors, because I'm introducing a positive charge. There's actually a hole. I'm creating a hole because I'm saying, okay, silicon, you only use 3 of your electrons to pair with my aluminum or with my gallium, with my indium. It depends on what dopant I'm using. Okay, and that sounds quite easy. I'm sure you guys already knew this somehow. Now let's look at the band structure. If we think of the band structure, it's actually the same. And in most books, you will find the band structure for extrinsic semiconductors as similar or as the same one as that for intrinsic semiconductors. However, that fact of having some impurity atoms present actually sort of pushes, right, researchers and physicists to say, okay, how can we represent this? How can we actually say it's not the same, because we actually have other atoms, right? We have impurity atoms in my structure. So how can I introduce those impurity atoms? And actually, for that, they decided to come up with this concept of an impurity state that is not really a state, but at least it helps to understand how the band structure will be somehow modified. So, and what you introduce in that is this. You see this level right there that is actually a dash with a dash line, and the level right there. Well, those are called, obviously the upper one will be the donor level, and in the case below that will be the acceptor level. So the distance between them and the conduction band actually is not really that you have a level there, right? Well, let's say it's actually not. It's not like actually your conduction band is increasing, right? Or your valence band in the case for the p-type semiconductors. It's not really that your valence band is increasing, right? It's just a level that conceptually has been introduced, so we can understand that now the energy that is needed to transfer the electrons into the conduction band is a bit lower, right? Why? Because, well, before, let's say in an N-type semiconductor, this is just again to represent what's happening when I'm doping my semiconductors. Is that okay? My electrons are here in the valence band. Now they don't need really to jump to the conduction band all the way through. They can just go to the donor level. They just need to jump to the donor level, and that's it. From the donor level, they can easily get to the conduction band. It's the same here for p-type semiconductors. Now electrons don't really have to jump from the valence band to the conduction band. That's no longer that doesn't longer happen. They automatically get promoted. It's like an automatic promotion to the acceptor level, and now they only need to jump from the acceptor level to the conduction band. So please bear in mind that these levels that you see there doesn't really mean that mobile electrons or holes are found in the forbidden band, because remember, this is the forbidden band that is supposed to be an energy gap. So it doesn't really mean that you have mobile electrons or holes there. It's just a representation, or what does the fact of having either donor or acceptor electrons does in a semiconductor. So it's just a way of representing, or a convenient way to show the presence of extra electrons or holes in a crystal. Okay. So far, so clear, guys?
Hi, I have a question.
Yes.
So, when I use donor or acceptor levels, I am actually reducing the energy gap between the bands.
It's not really that you're
I mean,
reducing the energy gap, because the energy gap will be the same, but you can say that electrons need less energy, right? There's not really a calculation, and again, for the purpose of quantum physics, actually the energy gap shouldn't change. But yes, you can definitely say that the electrons have an extra energy, right? Yeah, rather than reducing the energy, you can say that electrons or holes have an extra energy, so it's easier for them to jump into the conduction band.
so it's not actually an extra. It's not actually extra energy, but because there are more electrons,
It's
there
easy.
is it's easier. There is more probabilities for them to cross the energy gap.
Yeah,
Something like
rather
that.
than more electrons, I will say there are electrons that now are loosely bound to the atoms.
Okay.
Like in the case of intrinsic semiconductors, all of the electrons are well coherently bound. Whereas in this case, I have electrons that are not, or some electrons that are loosely bound, and therefore it's like, oh, they can start as I increase the temperature and I apply an electric field, they will start easily moving through the crystal. Whereas I need more energy if I want to move electrons that are coherently bound and well bound to an atom, like in the case of intrinsic semiconductors. But yeah, that's a concept. This is more just an idea of how can we understand what's happening. But yeah, in general, you can say that you have more electrons that are loosely bound, or you have electrons that are loosely bound to the atom, and that's why they can move easily in the crystal and obviously jump to the conduction.
And that's why the conduction band lowers. Like,
Again, the conduction
I
band
mean,
will remain there.
it's not
Yeah.
in a conceptual. I don't know if
Yeah,
that
definitely.
word exists, but
Yeah, you can say that. Yeah,
more of a concept.
or in p-type semiconductors, you can say the valence band goes up. Yeah, or in n-type semiconductors, the conduction band becomes goes down. Yes.
Okay.
Okay. Cool. Okay. Now, oh yeah. So this is just comparing intrinsic and extrinsic semiconductors, right? So let's say at 0 Kelvin, the excess electrons of the donor impurities will be in close proximity to the impurity atom, right? If we're talking an intrinsic semiconductor. Because at 0 Kelvin, I have no energy, I have no motivation. The electron is there and it doesn't have that extra motivation of energy coming from outside, so from temperature. So the electron will be there. Yeah, it will be, it's not bound strongly, but it's there. It's just in close proximity to the atom. But when I start increasing the temperature, and that's what you see here, right? And that's why it becomes so difficult. So for let's say intrinsic semiconductors, I actually need a temperature. This is in general, right? It will vary from what semiconductor I'm talking about. But let's say one example, let's say silicon. I will need 300 Kelvin before I actually increase my number of charge carriers, right? So I need 300 Kelvin to get obviously a high N and therefore a high conductivity. Whereas in an extrinsic semiconductor, it's only at 0 that I have a very low number of charge carriers. But as soon as I start increasing the temperature, so look even at 100, what happens at 100 Kelvin? I already have a number of about 10 to the 15 number of electrons per centimeter cube. That's quite a high number, right? And that's a good number for a semiconductor. And obviously that will remain. And you can see actually that the higher, and this is very, very important. So the effect of an extrinsic semiconductor is actually seen at low temperatures, and low temperatures being up to around 300 or so. Because if you realize up to 100, you have a step increase, like a very marked increase in the number of electrons, and therefore that means an increase in conductivity, right? And then you see it sort of flats out. Sort of flats out, so it does increase, but very slightly. And then actually, the effect that dominates there, it becomes the intrinsic, right? So around 300-ish Kelvin, it's all the intrinsic effect that dominates. So this is to say that the extrinsic effect actually has an effect only at low temperatures or temperatures below, let's say 300-ish Kelvin. That is when actually the extrinsic effect in extrinsic semiconductors or in semiconductors is valuable. After that, it's actually like having an intrinsic semiconductor. So having an extrinsic semiconductor after 300 Kelvin, it really doesn't have any significant effect, because it basically behaves as an intrinsic semiconductor. It basically, from there, at 300 Kelvin, I'm already giving enough energy for a lot of electrons to jump, even if I wouldn't have those extra electrons or extra holes that I have when I dope my semiconductor. Is this clear, guys? So basically, when you see this increase, and this is something it says here, if you read this part, right? This increase is actually basically, I achieve that once all my electrons, but all those electrons that are free, right? Or all those electrons, say not free, but that are loosely bound. So if I introduce a dopant, okay, all those electrons that now are free, are loosely bound to their atoms, okay, all those electrons will be excited into the conduction band. And that's why I see that increment in the number of electrons. If I further increase the temperature, you see the curve practically levels off until I get actually the intrinsic effect. That is, remember, I get high enough energy so that I actually can make other electrons that are not loosely bound, but just not any electron, but electrons that even if they are closely bound to their atoms, I'm giving them so high temperature, that means room temperature, that they can have enough energy to jump into the conduction band. But remember, that's just the intrinsic effect, right? So I will get that in an intrinsic semiconductor as well. Okay. So the conductivity in an extrinsic, of an extrinsic semiconductor will be basically the same, or I can calculate it the same way as that for an intrinsic one. Right? The thing is that if I'm considering only room temperature, then I need to consider only the majority carriers. So that means, for example, this, right? Conductivity, same equations, N, E, and mu. Mu is the mobility of the electrons, that hasn't changed, right? In this case, let's say that holes don't really influence a lot. In this case, actually, mu of E is just the number, is the mobility of the donor electrons, right, in the conduction band. And ND of E is the same, is the number of donor electrons, right? Because that's just the big effect. That's just what matters at this point. So basically, we can safely assume actually that at room temperature, mostly all donor electrons will be excited from the donor levels into the conduction band. That's why we actually, instead of using the whole number of electrons in the conduction band, we can just say the number of donor electrons, because that's basically what's contributing in this case in extrinsic semiconductors to the electrical conductivity of the material. Okay? And we can say that, okay, NDE, so the number of donor electrons is actually the same as the number of donor atoms, right? Because, well, that makes sense. Remember, there is only one electron that is free, right? Either if it's a group 3 or group 5, well, I have one hole or one electron free, right? So depending on the number of atoms that I introduce, it will be the same number of electrons or holes, right? Okay, questions? Now let's see what happens with different doping levels, right? So for low doping rates and low temperatures, the conductivity decreases with increasing temperature. And that's something is happening here. By the way, yeah, this will be, sorry, low doping rate, and that will be high doping rate, okay? So for low doping rates, and if you're at low temperatures, actually the conductivity decreases up to a point with increasing temperature, right? So that's basically the same case as metals. Why is it happening? What happens in metals when you increase the temperature? Mobility gets reduced, right? Because you have a higher number of lattice vibrations, and therefore you have more collisions, and therefore you decrease the mobility. So that's what's happening. So basically, you have phonon scattering in this region if you have a low doping rate. So at low doping rates, low temperatures, you basically have a metallic behavior. But if you increase the temperature, so if we are at room temperature or higher, remember now we have that effect of the intrinsic case. We now have that intrinsic effect. And that obviously, remember that we have that at room temperature, remember that we have that competition, right, between mobility and number of electrons. But remember, as we said, that what gains the battle is the number of electrons. So N gains the battle, and therefore you start seeing this increment. Whereas for high doping rates, so because you just have so many electrons or holes that you introduce, you don't really see that decay. You don't really see a significant decay, even if it's a high doping rate, because you have so many electrons. So even if there are more scattering, or if there are a lot of scattering, well, you also have a lot of electrons or holes that are moving, so you don't really see a scattering. And then once you go at high temperatures, remember, it's the same, right? You start seeing intrinsic effects. So then it obviously will start increasing. The conductivity will start increasing. It's obviously less pronounced, but you still have an effect. Okay? Questions, guys? Is it clear, everything?
Yeah, for me it's not clear. I mean, I have low doping rates, low temperatures. I am in the, for example, where they says phonon scattering point at that region. Okay, that is low doping and low temperature. Then, when I increase the temperature, the conductivity must decrease. But
no. Remember this. We're in semiconductors. We're not in metals. Remember this. Conductivity depends on this, on the number of charge carriers and the mobility. So yes, mobility decreases, but the number of carriers increases. And remember, at the end, overall, what gains?
It will become an intrinsic semiconductor.
Yeah. It's not that it becomes an intrinsic semiconductor, but the intrinsic effect is actually what dominates. Yes. Because you just have so high temperature, so room temperature, that you're giving a lot of electrons that energy to go and jump into the conduction band. Yes, you will have scattering for sure. That's why mobility will decrease as well, for sure. Mobility will decrease. But you're just giving so many electrons that energy to jump into the conduction band that overall, N increases, mu decreases, but this actually increases a lot more than what this decreases. So overall conductivity increases.
But we're going through from 0 point, for example, I mean,
Yes.
I wanted to say that in, okay, we are from at 300K.
Yeah.
Okay, and we're moving to 500K.
Yeah.
Although I have intrinsic effects, the curve that I am seeing is going upwards.
The what? The core you said?
The curve, I mean the line, the graph.
Yeah. Okay. Yeah. It
So that is,
must go up. What do you mean? Because this is conductivity. So conductivity must increase. The y-axis is conductivity.
but you're saying that the conductivity decreases.
No. No, I didn't
Yes,
say
in the I mean the slide is written for low doping rates and low temperatures. For example, the conductivity decreases with increasing
yeah,
temperature.
here, in this. Low doping rate, low temperature. This is low temperature.
Yes.
This, in this case, look at that region. Is it decreasing or not? That's why I was saying this region, the phonon scattering region. Because in that case, I have low doping rate. So that means I don't have a lot of extra electrons or holes, right? It's just a small number. And because I'm at 200 Kelvin, I have enough energy, or it's different than being at 0 Kelvin, right? When I have no mobility. So I'm putting some energy, 200 Kelvin, that's some energy. But because of that energy, okay, everything starts moving. So I will have more collisions. And because I don't have a lot of electrons or holes to move, therefore, actually so I have a small number of N, and mobility is decreasing. Because obviously, there are a lot of collisions and lattice vibrations. And therefore, overall, in this region, conductivity decreases. But it's just in that region. So the curve B is low doping rate. Curve A, so the above curve, is high doping rate. So for low doping rate and low temperature, yes, I will decrease. I will have a decrease in my conductivity. But as soon as I reach around room temperature, so around 300 Kelvin, intrinsic effects start setting in. Because I'm giving so much energy to electrons, so they can actually start moving a lot and they can start jumping into the conduction band. And so N is not gonna be small anymore, even if I have a low doping rate. Because remember, intrinsic effects don't depend on doping rates. They are intrinsic, right? So N is not small anymore. N is actually big now. And yes, mobility will decrease for sure. But now this effect is bigger, and therefore conductivity will increase. And that's why you see now an increase in conductivity. Is now clear or not?
Yes. Okay. Now it's clear. Thank you.
Cool. Okay, so now remember we said that for intrinsic semiconductors, actually, the energy gap is halfway through the Fermi energy is halfway through the energy gap, right? And that makes sense, remember, because we said at the end the same number of electrons must be equal, or the number of electrons that are found in the conduction band must be equal to the number of holes in the valence band. And that makes sense because we don't have any extra electrons, right? So that makes sense. But that was for the intrinsic case. Now, what happens for the extrinsic case, right? If we go, let's say, to an N-type semiconductor, I think it makes sense to think, and that is actually true, that more electrons will be found in the conduction band than holes in the valence band, because I had extra electrons, right? Because it is an N-type semiconductor, so I put extra electrons. So it makes sense that I will have more electrons in the conduction band than holes in the valence band. Especially that happens again because the extrinsic effect actually has a big effect only at low temperature. And remember, low temperatures, I mean 0 to 300 Kelvin or 250 Kelvin, okay? So that is when actually we can say, oh, actually we have more electrons than holes in the conduction band. Sorry, more electrons in the conduction band than holes in the valence band. Therefore, actually, the Fermi energy is not now halfway through. So the Fermi energy is actually not exactly, especially at low temperatures, is not really the value of half of the energy gap. It's actually between the donor level and the conduction band. So it will be somewhere, my Fermi energy value at low temperature especially will be somewhere there, between the donor level and between the conduction band. As I increase the temperature, remember, everything just becomes like an intrinsic effect. Therefore, as I increase the temperature, actually, my Fermi energy value will start decreasing until it eventually reaches the value that we'll have in an intrinsic semiconductor, so halfway through the band gap energy. And the same will be for a p-type semiconductor. In that case, let's say my donor level is here, so my Fermi energy at low temperatures will be somewhere here, right? And then eventually, if I start increasing the temperature, it will eventually reach the value of half of the band gap energy. Does this make sense? Is it clear, guys? Okay. Time to jump. This is enough for semiconductors, right? So we've already seen superconductors. Well, conduction in metals, alloys, superconductivity, semiconductors. Now it's time to enter into conducting polymers. And these conducting polymers, metal oxides, and these things, it's not going to be so in depth as the previous ones we saw, right? We just finished, let's say, the main part of electrical properties. But it's still relevant to talk about, okay, how does conduction happen in polymers? How does conduction happen in ceramics? And that's something we're going to talk about right now. Okay. Obviously, it won't be an in-depth explanation, one, because there's still no a clear and definite explanation. There's still a lot of research ongoing on what's actually happening at the quantum level, right, in conducting polymers and in conducting ceramics. But there are a few theories that are valid, and we'll see a bit of that. Okay, so I mean, it's not a surprise, or probably it might be, but hopefully it is not, that such as we have some conducting ceramics, there are also conducting polymers. Yes, most polymers are not conductors, that's true, but a lot of, well, not a lot, but a few of them are conducting. And actually, when they started to be synthesized around 1950s, I believe, they were actually very unstable in air or above room temperature. And also, a lot of the dopants that were used to give the polymers conductivity, electrical conductivity, they were very toxic. Right? Recently, lots of research going and new technology and everything. So there have been new processes to synthesize polymers. And among those, actually, we have the P dot. P dot is so far is the best known conducting polymer, and a good thing, as we'll see, is actually non-toxic. It doesn't, you can actually dissolve it easily, so it's a nice polymer, okay? And it's actually, that's why it's actually produced in tons around the world, right? Where is, or where are these polymers used? Well, for a lot of things, actually. Some of the uses are friction-induced static electricity. That's probably the most typical use of these conducting polymers, right? Then we also have inorganic electroluminescent devices, anti-static treatments of plastics, cathode ray tubes, electrodes for capacitors, for sensors, rechargeable batteries. There are some trials ongoing to see if we can have photovoltaic devices with conducting polymers instead of silicon or semiconductors. That's an ongoing field. And then also for packaging of electric components, where you don't want in some electric components, you don't really want to have an insulator, but to have a conducting polymer. So that's where they use it, right? And the advantage of PDOT compared to most other conducting polymers is that it can actually be heated up to 100 centigrades for more than 1,000 hours, and it will hardly lose any conductivity. So it will basically remain, or it will basically have the same conductivity as it will have if it's at room temperature and indefinite time, right? So that's why I said this is actually the most used, or the currently most used conducting polymer in the market. Okay. But, okay, time to just not focus on that one, but let's just now sort of expand the concept and go a bit more basic and see what happens with conducting polymers. So, interestingly enough, most conducting polymers have a temperature dependence, right? Like metals do, like semiconductors do. And actually, they have a similar behavior to semiconductors, and therefore, semiconductor theory can be somehow applied to conducting polymers. Yes, we need to modify certain things about band structure and the band model, because they are polymers, they're not crystals, they don't have a nice arrangement. There are obviously a lot of things that will limit how a polymer behaves as compared to a semiconductor. But again, the basic theory of semiconductor conduction can actually be applied, and just because they do behave similarly, it can be applied to conducting polymers. Yes, they are amorphous, they are mostly non-crystalline, or just a mixture of crystalline and amorphous regions, but yes, so we need to modify that concept, but we can apply the same theory. So remember, polymer, they have chains quite long, right? They have macromolecules, they have the monomer, and then that monomer goes and repeating on and on and on, and it forms the polymer, right? The forces that hold those atoms, the atoms inside the monomer, and obviously that holds also the repetition of those monomers, are usually covalent, sometimes ionic, but most of them are actually covalent. Sorry. However, within the polymeric change, within the polymeric chain, we know that the secondary interactions, so the interactions between macromolecules is actually quite weak, and we know that they have sort of secondary binding, sort of like van der Waals type binding, right? So if we're talking about this structure of polymers, that it has a monomer, a repeating unit, And we know that the interaction between macromolecules is not as strong as it is within the polymer, within the monomer itself. Well, for that, we can sort of try to relate or modify our band theory based on that. And so if we're talking about that, we actually need to know the degree of order that the polymer has in order to consider band theory, because we know the more ordered the polymer is, obviously it will behave more like a semiconductor, right? Because it's only ordered molecules that usually are strongly interacting molecules, and therefore they are the ones that will be, or the electrons that are there, sort of joining those molecules are the ones that might help to conduction, right? So basically, we can say that there is a dependence on the order or the conduction of a polymer on the order of the molecule. Let's talk about the simplest conducting polymer known. That is, polyacetylene. It has a very high degree of crystallinity. And to be a polymer, it actually has a relatively high conductivity. You can see there the conductivity of certain polymers, considering some, because of some weird considerations, graphite sometimes is considered as a polymer, but let's forget about that. But then you can see Teflon, polyester, very low, completely insulators, right? You have nylon, and then you have these interesting forms of polyacetylene. You have the cis polyacetylene and you have the trans polyacetylene. Okay, the values you see there are conductivities of polymers. So, as I said, polyacetylene is the simplest conjugated organic polymer, and to be so simple, it actually has the highest conductivity of all the simple polymers that have been synthesized. So, it has two principal isomers. It has the transform, the one up there, where I have the hydrogen atoms alternately bound to opposite sides of the carbon. So I have on one side and on the other, and on one side and on the other. Whereas in the cis form, I'm sure you might have learned that this, the hydrogen atoms are all situated on the same side of the double bond carbons. Right? If you just compare the properties, actually, trans polyacetylene is very silvery and flexible, whereas cis polyacetylene is more brittle. Well, that silvery flexible film, so trans polyacetylene, actually has a conductivity that is similar to that of silicon. It has 10 to the negative 4. Okay, the pure trans polyacetylene, around 10 to the negative 4 ohms per, well, 1 over ohm per centimeter, right? So, I mean, it's in the range of semiconductors, right? Now, so let's look at the band of that material. The thing in polymers is that it actually, the distance between carbon atoms has a big effect. So, you know, polymers, they do have this, right? Carbon, 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 and then, you know, hydrogen, and then the double bond. So you know all that. In polymers, this distance, they are all not the same, unfortunately. If you consider that all carbon bond lengths are equal, you actually will get a band structure like for a metal. If you calculate, if you were to calculate the band structure, you will get something like figure A. So that is like the band structure for a metal. You see pretty much overlap of all the energy bands, and so you will get a tremendously nice conducting polymer. Right? However, this is not true. Not all carbon bonds are equal in length. And not only in polyacetylene, but in general, in polymers, it's very difficult to get that. And so when you calculate that, so when you calculate and adjust the calculations for that reality, you can start seeing, for example, for B is for a small modification of certain carbon bonds, and C is actually for a more real modification of the carbon bonds in transpolyacetylene. And you can see something quite interesting. It's actually the same or similar band structure that you will get for a semiconductor or an insulator. Look at that. You do have an energy gap. You do get a region where there is a higher band and then a gap and then the lower band of the next layer. So you do have a gap. And that gap actually will depend, and that is why it's so complicated to make calculations for polymers, because the width of that band gap actually depends on the extent of alternating bond lengths. So basically, how much are the bond lengths varying? And you know, it's so difficult to synthesize the same exact polymer so that all bond lengths alternate the same way. So, you know, you might have synthesized one that varied, I don't know, let's say 1,000 bonds. In another one, you vary 10 to the 5 bonds. And so it's so difficult to get the same completely structure. And therefore, you will get a different band, a different length in your band gap. That's unfortunate, but that's the reality in conductive polymers. So look at that. The bond, the extent of the bond, actually, does have a big effect on the gaps that polymer has. And obviously, if you get a polymer, a completely random polymer, like a completely amorphous polymer, where you have a big variation of bond lengths, and obviously you will get a huge band gap that is basically an insulator, and that's why most polymers are insulators. Is this clear so far, guys? So therefore, if you decrease that disparity of carbon bond lengths, actually you will increase the conduction because you will reduce your band gap. And that's why you will not have a table like for other materials that we saw that you actually have, oh, this is the value of the band gap. You will not get it because you might get a big variation or a small variation in carbon bonds from one process of synthesis to another, and you know, it's already a variation, and that will have an influence on the energy gap. So now that is one point, okay. Now let's actually see, okay, but what electrons are the ones that are contributing? Because if we're talking about conduction, we need electrons, right? Well, if we're talking specifically about conjugated polymers, like polyacetylene, right? We have the double bond, carbon to carbon, right? Well, in those polymers that actually are most of the polymers that are conducting have these double bonds between carbon to carbon. The electrons that are there in that double bond, actually, they are considered, they are called p electrons because they are considered to be loosely bound to the neighboring carbon atom. So when you have this double bond carbon to carbon, the electrons that are there are considered to be loosely bound. And therefore, those electrons, once you increase the energy, because it's the same behavior as in semiconductors, once you increase the energy, those are the electrons that under an accelerated electric field will be able to travel and jump into the conduction band and therefore contribute to conductivity. Okay? And you dope them. Yes, you can definitely dope them. You can increase the conductivity by doping in semiconductors, while you can dope your polymers and it will also increase the conductivity. And for example, this is the case for arsenic pentafluoride transpolyacetylene. So in transpolyacetylene, you dope it with arsenic pentafluoride. And look at that, you get a conductivity of about 10 to the, I would say even close to 500 1/Ohm per centimeter. Just quite a nice value of conductivity. I mean, that would be the conduction of a poor metal, right? Of like a poor metallic conductor, that would be sort of the same. So it's basically around what a conductivity of a dope semiconductor will have. Maybe a bit lower, but around that. And depending on what type of dopant you use, well, again, you will have N-type or P-type semiconductor. Well, in this case, will be polymer, but it's basically the same. It's the same principle. So look at that. You can actually increase by what? What was the conduction? So you have a conduction of around 10 to the negative 4, and you can jump to a conductivity of around 10 square. So about 6 order of magnitude improvement just by doping. Okay. Remember that doping in semiconduction, and this is just something important, I guess. When we're talking about semiconductors, doping really means addition of impurity elements, but really small additions, right? Whereas here, doping will mean actually a lot of dopant, right? So, for example, arsenic pentafluoride transpolyacetylene will have around 30% of dopant. Whereas, you know, in a semiconductor, you dope with 0.01% or 0.12% at maximum, right? So it's very small additions. Whereas here, doping means a lot, around 20 to 40% of dopant. Okay, is it clear so far? Okay. We need to describe or mention an extra concept to describe the conduction in polymers. And that actually is called a soliton. Yes, it does apply perfectly for polyacetylene, but it doesn't only apply to polyacetylene, but in general to most conducting polymers. And that is the concept of a soliton. What is a soliton? So, a soliton is just a structural distortion in a conjugated polymer. Remember, conjugated polymers are all these polymers. So in a conjugated polymer, and it generates when a single bond meets another single bond. And you're going to tell me, wait, what? How does that happen, right? So there will be a point in this conjugated polymer, right, that you will have because of something, and usually it is because of doping, you generate this. You see? You sort of break the structure and you generate a single bond to a single bond connection. Well, at that point, a distortion happens, right? At that point, there is sort of a localized non-bonding electron state is generated, because obviously, look at that, carbon is only bound to 3 other elements, right? There's missing one. So that's a localized non-bonding electron. Like it happens in an n-type impurity, right? Same principle. So that is a soliton. That fact that because of an impurity, you sort of break the structure, that's not really break, but you're sort of leaving one electron free. Okay? And well, that is called a soliton. That combination of events, let's say, that is called a soliton. And obviously, it's basically as an electron, so it has, or it's associated with a negative charge. How does that affect my band structure? Well, the result is actually a localized level, a very small localized level around the center of the forbidden band. Okay. And now, once you start forming a bunch of solitons, because once you form one, it's like really the polymer really likes that, and will start forming another one there, another one there. And obviously it does have a sphere influence, right? Because the effect is not just localized, it sort of affects the surrounding of the polymer. And therefore, you actually start getting an additional contribution to conduction, and that actually is, or that's how that's what they call a metal-like conduction. Okay? Because now you have an additional effect, let's say, that contributes to conduction in polymers. It's just, again, the soliton is just a concept of, because of doping especially, sort of disturb the structure, leave one electron free, and that generates a soliton. Here you have different conducting polymers, polyanyls, polypiperols, polythiopines, polyphenylines. The derivatives, all of them are conducting. Unfortunately, most of them are toxic. Others that are not toxic but are insoluble. And as I said, we have the P dot that is the great one. It's water soluble, it's environmentally friendly, so the best polymeric market for if we're talking about conducting polymers, right? Now, talking about real applications of polymers, I already said and I already mentioned some applications of conducting polymers, but now looking further, trying to replace metals with lightweight conducting polymers, especially for wiring. You know, in wiring, metals are the best choice and top choice, right? Trying to do that actually, at this moment, it actually seems impossible. And that is because mainly a lot of polymers are very poor or in stability, so they are very reactive. Luckily, we could say that this drawback for certain applications is very beneficial. For example, in gas sensors, in biosensors, or other remotely indicators that can detect changes in humidity, in radiation, in some mechanical abuse or some chemical release of a component. Because obviously that actually helps, because okay, if my wiring, let's say, is not stable, yeah, I will actually start seeing if let's say there is a change in humidity, right, or a change in radiation, it will actually start degrading my polymer, and I can actually say, oh, okay, I see a change. and obviously let's say it will ring my sensor, but at the end I'm saying, okay, it actually works. Because the problem in metals, let's say using metallic sensors, is that, because they are so stable that you don't really know, or it's difficult to actually check or to actually see, even if it's a small change, or especially if it's a small change either in humidity or radiation. It's very difficult to detect that. Whereas if I have a polymer and they're not stable, they're quite reactive. Even if I have a very small change in humidity or radiation, I can actually see that and say, oh, okay, there's actually a change. I can obviously measure that, and that will be a bit more effective and more visible. But yeah, other than that, it will be quite difficult to replace, at least for now, conducting metals, especially metal wiring, with conducting polymer wiring. Okay. Questions? Okay. Let's talk about ionic conduction now. And if I'm talking about ionic conduction, it should come to your mind that, oh, okay, so you're talking about one type of ceramics, right? Because remember, most ceramics do have this behavior of ionic bonds, and therefore, actually, they do have ionic conduction. So, what happens in ionic conduction? Okay, the individual lattice atoms transfer electrons between each other, right? That happens in ionic crystals. You have positively charged cations and negatively charged anions, and they are transferring electrons between each other, right? And we all know ionic binding is so strong. Therefore, that's why the room temperature of all ionic crystals is about 22 orders of magnitude smaller than the conductivity of typical metallic conductors, because, and remember this from ceramics, we have ionic conduction so strong, so stable, ionic bonds so strong, so stable, that obviously they are poor conductors, because all the electrons are extremely well bound and connected, because of that difference in electronegativity, right? But actually, the main contribution to the electrical conduction in ionic crystals is ionic conduction. And what is ionic conduction? Well, ionic conduction is just caused by the movement of some either negative or positive, depending if we're talking about cations or anions, that hop or that jump from one lattice site to the lattice site under the influence of an electric field. So basically, let's say in simple terms, ionic conduction is like electron conduction. So electrons are moving in semiconductors, in metals. Well, in ionic crystals, ions are moving. Yes, obviously they're not so mobile. It's not the same effectiveness as having electrons moving and therefore having perfect electric conduction, but it's the same principle. It does apply the same. Ions hopping from one lattice side to another lattice side under the influence of an electric field and jumping back and forth. There is a small thing to mention there, and I'm gonna do it in the next slide. Okay, so now let's and before doing that, let's see the equation, right? Because I mean, we already said, and that's why I said this relationship applies for everything, and the only thing that will change is just the meaning of the terms, because electrical conduction is the number of charge carriers, the charge, and the mobility. In this case, if we're talking about ionic conduction, well, it's the number of ions that are able to hop or to jump from one lattice side to another lattice side, the charge of those ions, and the mobility of the ions. So same equation, same principle. For ions to move through a crystalline solid, they do need sufficient energy, like electrons do, right? Remember, electrons, they do need, for example, that extra energy from, let's say, from increasing temperature to be able to jump, right? From the conduction band to, sorry, from the valence band to the conduction band. So same principle here for ions. They do need enough energy or sufficient energy to move. And actually, in ionic conduction becomes so interesting because it actually, they actually need, it's not like electrons, let's say, at least the movement of electrons, we're considering jumping from the valence band to the conduction band, right? Here is actually a consideration of more like a moving from one lattice point to another lattice point. So we're not really talking here, and this must be clear, from a band to another band. This is actually within my solid, hoping or jumping or moving from one lattice side to another. And to do that, they need to actually overcome an energy barrier. And that's what you see in the graph, for example, there. You have a schematic representation of the barrier, the potential barrier, that concept comes again, the potential barrier that an ion has to face, or an ion has to actually face and overcome in order to move, in order to exchange. And actually, where are they moving? Where? They are actually moving to a vacancy site. So the black dot is an ion, and the empty square or the white square is a vacancy. So if we don't apply any electric field, well, they do need an activation energy, that is Q right there. They do need an activation energy to move, to overcome that energy barrier and move from this lattice side to this other lattice side where actually a vacancy is sitting. Okay. So they need enough energy to overcome and move that ion to the vacancy side. Therefore, as you can imagine, actually this term, the number of ions, depends on the vacancy concentration. And that is actually something quite important for conduction in ionic crystals. The number of vacancies. I'm not sure if I'm sure you've learned at some point that the number of vacancies is related to the Scott-sheet effect. I think you should have learned that in one of your previous courses. So now, if we're talking or we're saying, okay, ions moving from one side to another side in my lattice, and actually moving from one place to a vacant side in my lattice, well, that's actually diffusion, isn't it? Just diffusion of ions, right? Well, if it is diffusion, then I can definitely relate the mobility of the ions with the diffusion coefficient through Einstein relation. So the mobility of ions in this case can actually be explained with the Einstein relation. Right? T is the diffusion coefficient, the charge, volume, and constant temperature. And that diffusion coefficient, actually, we all know that it actually depends on temperature, and we can express that dependency with the Arrhenius equation that I'm sure you guys all know, the Arrhenius equation. So D naught is just the pre-exponential factor, right? It's just a constant. Can you combine both equations? Yes, for sure. I can combine both equations, therefore, and that I will get an expression like that for the conductivity in ions or ionic conduction. Okay, I can simplify this. I can make things easier because I can realize that these terms are mostly, or I can associate all these terms in a sigma naught term. And if I take the natural logarithms of that equation, I get something like that. right? Like typical of an Arrhenius equation, as you might know. So what's happening here? Look at that. Well, it tells me that there should be a linear relationship, right? Between the conductivity, well, the inverse, the logarithm of conductivity and the inverse of temperature. And actually there is. There is a linear relationship. And actually, if you look at the graph, you can notice two temperature regions representing two different activation energies, because remember that if you just look at the equation, you can definitely say that the activation energy is related to the slope of the line, right? You can definitely see that. Therefore, this linear relationship can tell me, or I can see that there are two regions of temperature, and therefore two regions of two different activation energies, because I can see two slopes there, right? There are two slopes. So at low temperatures, what's happening? I don't see a big slope. So actually, the activation energy therefore must be small. What does that mean? Well, the thermal energy is just sufficient. So what do I mean? It's not high enough yet so that only a few ions can jump into the vacancy zone. Well, that region is called the extrinsic region, just making an analogy to what happens with semiconductors. However, once I increase the temperature, and remember what happens at high temperatures in semiconductors, it becomes the intrinsic effect, right? So the same here. At high temperatures, I have so high thermal energy that I can create additional vacancies. And the activation energy for ions to move to those vacancies is actually lower. Therefore, I have a higher activation energy and I have a bigger slope, in that I'm falling into the intrinsic region. So, well, is this clear so far? Okay. And that is the big difference between stoichiometry and non-stoichiometric compounds, talking about ionic compounds, right? Because if you have stoichiometric compounds, then you can only form vacancies at high temperatures, whereas non-stoichiometric compounds have already, because they are non-stoichiometric, they already have a high amount of vacancies even at low temperatures. So, and therefore they will have a higher conductivity, right, at low temperatures. How can you introduce vacancies? Well, you can also dope, right? And that's actually something that happens in metals. For example, in ceramics. Let's say you have zirconia, and you introduce calcium oxide, right? So zirconia, remember zirconium has a valence of 4, and you're just introducing calcium oxide. Well, calcium just has a value of 2, so you're just substituting 2 ions out of 4. Therefore, you are creating 2 vacancies, right? So it's the same concept as doping in a semiconductor. Okay. Now let's talk about conduction in metal oxides. Okay, that are also ceramics, right? Metal oxides are one of the groups of ceramics. And that, let's say, especially those that don't have this ionic behavior. Well, this is basically something we saw, and I would say I already taught in ceramics. So I'm just more like a review of that. Okay. Metal oxides can be either conductors, semiconductors, or insulating. And what's the magic about metal oxides? It's the oxygen itself, right? Because oxygen has 4 2p electrons. If you look at the electronic configuration, it has 4 2p electrons in its outermost shell. So if I bring 2 more electrons, I fill the p shell, right? And therefore everything gets filled and nicely arranged, right? And that's, for example, something that happens in titanium dioxide, right? If you remember the electronic configuration of titanium, well, the important part is that it finishes in 3d(s)2 and 4s2, and this, again, this is something we saw in ceramics. So if I'm talking about titanium dioxide, well, I need to use these 4 electrons there, and therefore the 4 electrons that are provided by titanium are taken, or are basically are taken all by the oxygen, and therefore they all occupy. There's nothing free there, and it's basically a noble gas configuration. And because it is, or they are at ionic bonds, well, they are so strong that if I want to get electrons away from there, I will need a considerable amount of thermal energy. Therefore, and that's why we saw, remember, that titanium dioxide is an insulator. But remember, we saw the case for titanium monoxide. What happens there? Well, I'm only using the two electrons from the 4s2, right? And the other 2 are free. So I have 2 titanium electrons that are free to serve as a conduction electron. And that's why titanium monoxide has actually metallic properties, or we can say is a conductor. Well, a poor conductor, but it is a conductor, right? It can actually get up to 10 to the cube, 1 over ohm per centimeter. So it's quite a good number, right? Considering it's a ceramic. Now let's look at the balance, sorry, at the band. How does that influence the band structure, right? Because this is nicely understood, and I guess because we already saw this, this is nicely understood from even from previous course. And this is nicely understood because I'm just talking about electrons. Now, what happens with bands, right? So let's consider the same case, this titanium monoxide, right? If we're talking about bands, well, we can definitely say, okay, the oxygen is filled, the 2p band, the valence band of the oxygen, it gets filled because I'm giving those 2 electrons of titanium. So the 2p valence band gets filled. But the conduction, the 4s conduction band in titanium now is empty. Now, if I look at the 3d band of titanium, I know it's partially filled because it has only 2 electrons, and these are the 2 electrons that are free there, right? Because I need a total of 10 electrons to fill that. Well, it's partly occupied, it's partly filled, and therefore same behavior as a metal. Remember, partly filled band, empty conduction band, electrons free to move and jump. So it gets the behavior as metallic, and as a metal, and that's why we get this conductivity. And you can do the same for example, for many other metal oxides like zinc oxide, tin oxide. And let's say we can do the same also for nickel oxide and for many other oxides that are conductive. Okay. In nickel oxide, though, it's just like there is something that might get confused. In nickel oxide, if you look at the electronic structure of nickel, okay, you will realize that, okay, you fill with nickel and oxygen, you're filling the 2p band like you do it with the titanium monoxide, and you get an empty nickel 4s band, such as you get an empty 4s band in titanium. However, for nickel, the 3d band is actually 3d6. Okay, it's not 3d2 like you get in titanium. That 3d6, the fact that I have 6 electrons there, because I'm adding wave functions. If I'm not mistaken, it's 3d6. You can look up the electronic configuration. I might be confused, but it's more than 5. I'm sure about that. Therefore, so what happens with this 3D with this 3D band? So if I use the wave function, remember first module, if I use the wave function to calculate that, I will actually start seeing that there is no interaction between those electrons, because it's just because they are more than half of the band is occupied, because as I said, I have more than 5. Remember that the D level gets filled with 10 electrons. So because I have more than half of that level occupied, there's not really a big interaction between the electrons. And therefore, it actually makes my conductor, or sorry, my material an insulator. Even considering that I have a 3D unfilled level, or not full level, but because it's occupied by, or more than half of that level is occupied, well, that with quantum mechanics calculations that I don't want to get into that, you can realize, or you will see, that there's actually no interactions between those electrons. And therefore it gets so difficult for those electrons to jump, and therefore it is actually nickel oxide, a stoichiometric nickel oxide is an insulator. Whereas if you replace some nickel atoms, creating vacancies and making a non-stoichiometric compound, actually nickel oxide can become a p-type semiconductor, because it has that easiness, right? I just need something small to put there, like adding an extra element that can make my compound non-stoichiometric, and therefore now those electrons that are in the 3D level, that is unfilled, now they can actually start jumping and nickel oxide can become a p-type semiconductor. Okay, questions so far, guys? Is it clear? No clear? Okay, we're about to finish. Now we're entering into the last part of this, dielectric properties. And then pyroelectricity, Piso Electricity, but again, that's just quite short. We're not gonna explain in detail theories and what's happening there. So what is a dielectric? I'm sure you guys know insulators are usually called dielectric, right? And the fact that, well, we're talking about electrical conductors, and conductors are great. They help to conduct electricity, very nice. But what happens with insulators then? So insulators serve for nothing? Well, not really. Actually, insulators have certain additional or nice properties that are very useful, especially in the electronics industry. And that is, for example, what some insulators have, some dielectrics have. So let's say you apply a voltage to 2 parallel metal plates, so to 2 conductors, right? You apply a voltage to 2 parallel metal plates. They are separated by a distance. The resulting electric charge will remain on those plates. Even if I remove the voltage, the charge will remain there. As long as air is dry and I don't have humidity and everything, I will keep my charge in my plates. So the ability to store an electric charge is called the capacitance, right? And I'm sure you've learned that from your previous courses. So the capacitance is basically defined as the charge Q per unit applied voltage. So, right. So I'm sure you guys learned that. And as you can imagine, the capacitance is higher the larger the area of the plate, right? And the smaller or the shorter distance between them. So actually, you do have this relationship of capacitance. The bigger the area, the smaller the separation between them, it will be higher. And that makes sense, right? Now, It's not so linear. Actually, there are these terms that are that also allow me to relate the capacitance with the area and the separation of the plates. Okay, what does epsilon and epsilon not mean? Well, epsilon basically determines actually the magnitude of the added storage capability. So it's basically the dielectric constant. Okay, I'm sure I've mentioned that term before. And epsilon naught is just a universal constant that its value is 8 times 85 times 10 to the negative 12 farad per meter. You can Google that. You don't have to memorize that. I will give you, if I ask a question on this, I will give you that value, so don't worry about that. Okay, so it's just the permittivity of vacuum or the permittivity of empty space. That's epsilon naught. It's a universal constant, and epsilon is the dielectric constant, right? So there is this relationship of capacitance between area, or between the area of the plates and the separation between the plates, with this term of the dielectric constant and the permittivity of vacuum or the permittivity of empty space. Okay. So now if you look at this graph, right? If you look at the graph, you can say, or you can see that actually the capacity increases when a piece of a dielectric material is inserted between them. So if I insert between these conductors, between these plates, a material that has a high dielectric constant, so a material that has a high value of epsilon. By the way, these are the dielectric constants for certain materials. You see dielectrics, and those that have a very high dielectric constant actually are ferroelectrics as well, and we're going to talk about ferroelectricity. So if you introduce a material that has a high dielectric constant, you can see that the capacitance increases, right? Now, why does that happen? How is it that putting an insulator, right, because it's basically an insulator, a dielectric, how is it that putting a piece of a dielectric between two conductors actually increases the capacitance? Right? Well, let's think, or let's go to the basics. Under the influence of an electric field, you know you have a negatively charged electron cloud of atoms, right? So let's say if you don't have any electric field, you will have like this. So you will have your nicely, you'll have a nice electron cloud, all nicely arranged without any disturbance. So your atom is in perfect condition. Okay. Your positive nucleus, you have the electrons outside, so everything nice. But if you have an external electric field, actually, that electron cloud, because it's negative, you know that the electron cloud is negative in charge, right? And the nucleus is the positive one. So actually, that negative electron cloud becomes displaced. So it basically moves towards the opposite end of the core. So it just goes or moves towards a position, right? That is actually opposite to the electric field. And it creates a dipole moment, as you can see. So the nucleus, it will be, let's say, above, okay? And then all the electrons sort of start or move to the opposite end of that. So let's say here, they will be below. Right? So you do create a polarization. You create a dipole moment. Okay, now, that formation of dipole, of all the atoms within the dielectric material, actually make or causes a redistribution of charge, so that the surface nearest to the positive capacitor plate is negatively charged and vice versa. So you can see, actually, in the graph here in the left, you can see the positive capacitor plate. And if you see, look at all the boxes, there are atoms, okay? So all the negative atoms, sorry, all the negative charges actually are towards the positive plate, right? And the opposite is true as well. So for the negative capacitor plate, you see the positive charges are at the right. Look, you see? All positive charges are at the right. So are the closest to the negative plate, right? Therefore, the electric field lines within the dielectric, all right, sorry, you create electric field lines within the dielectric. And obviously, these lines are opposite in the direction to the external electric field lines, right? So if, let's say, you are creating or you have an electric field in that direction, then you create electric field lines in this direction, like you do here, right? So all negative charges on one side, all positive charges on the other side, and therefore you have electric field lines that go opposite to the electric field, the external electric field, right? So those electric field lines within the dielectric are going to be weakened due to that polarization, right? That means the electric field strength in a material is reduced if I insert a dielectric between two capacitor plates. So the capacitance increases because I'm reducing the electric field strength. And why am I reducing the electric field strength? Because you see, you create internal lines or electric field lines because of the polarization that you created. Because the electric field is creating that polarization in my dielectric material. Therefore, the polarization is responsible for the increase in charge density above that for vacuum, right? So basically, if I have polarization, I will have an increase in charge density, and therefore I will have an increase in capacitance. Okay? By the way, this curve epsilon that you see there is the electric field strength. The electric field strength is defined as the electric field in vacuum divided by the dielectric constant. Okay? So that is actually called, to give it the full name, is called electronic polarization, because I'm polarizing electrons, or well, because of the cloud of electrons basically becomes polarized with the nucleus, so it's called electronic polarization. That actually happens in all dielectric materials that are subjected to an electric field. But if you have, for example, a dielectric that is also an ionic material, like alkali halides, you will have a process of ionic polarization. That is basically the same. It's just that cations and anions will be displaced from their equilibrium positions, right? So you have an external electric field and you will align, okay, cations on one side, anions on the other side, and that's it. Basically the same, right? As basically aligning or polarizing the cloud of electrons and the nucleus that is positive. It's the same here. Cations one side, anions on the other side, and you have this ionic polarization. And that happens in dielectric that are ionic materials. Okay? And then you have also another other type of dielectrics that, well, other than having electronic polarization because of an external electric field, they actually already possess permanent dipoles from their actual structure. And they are, for example, waters, oils, organic liquids, amorphous polymers, and one that you might remember from your ceramics course is barium titanate. If you remember the structure of barium titanate, you can definitely remember that central cation, right? And remember that central cation can displace, and that will generate a dipole that, remember, actually make the material dielectric, and remember that also makes the material ferroelectric, and we'll talk about that, but remember that from your ceramics course. So, well, that is called orientation polarization, or molecular polarization is the same, right? And so if a material has the three of them, so if it has electronic, ionic, and molecular, well, those three processes are additive. Now, you might be asking yourself, well, why is this useful? Well, most capacitors are used in alternating electric circuits. That means that they really need to reorient quickly under a rapidly changing electric field. Not all of these polarization mechanisms behave the same way, and you can actually see molecular polarization decays at very low frequencies, like 10 to the 10. Ionic can sustain the polarization a bit more, 10 to the 13, but it's actually electronic polarization. That's why it's the most important one, that can sustain frequencies up to even more than 10 to the 16 hertz. Therefore, that's why they are used, or dielectric materials are used in electric circuits. Because again, in an electric circuit, I really need to reorient my dipoles quickly under the electric field that is changing as it happens in an electric circuit, right? So that's why it's very important, or the main mechanism, or the most important mechanism, is electronic polarization. Obviously, there will be certain frequencies. A substantial amount of the excitation energy can be absorbed and transferred into heat, and therefore that will cause a dielectric loss, and that is a value for, or that there is a value for every specific material. So if we are using a dielectric material, we really need to know what that frequency is, because there will be a certain frequency at which basically I will have dielectric loss. Okay. Ferroelectricity. What is ferroelectricity? So certain dielectrics can exhibit a spontaneous polarization, as I said, that molecular polarization, that without the presence of an external electric field. Well, those materials are ferroelectrics. Those materials that show that spontaneous polarization and that can be changed, or where I can change or reorient that dipole, that polarization, by using an external electric field, well, that is a ferroelectric. So let's say I already have, right, a dipole. I already have a polarization. I come with an external electric field. I expose my material to that external electric field. Well, all those dipoles actually will start, or will start to align with the external electric field. All of them will start aligning with my external electric field. They will become parallel to the field until I get a saturation polarization. So I get this value. If I withdraw my external electric field, I will have a remnant polarization. And I need to invert my electric field until I reach a coercive field. Once I reach my coercive field, if I increase that coercive field, I can finally orientate the dipoles in the opposite direction. So if, let's say, they were in that direction, now I can orientate all my dipoles in the opposite direction, right? So basically I will be here. If I reverse field once more, so I go back and reverse all the field all the way, I can basically complete a loop, and that is a hysteresis loop. And that's why ferroelectrics can be utilized, for example, in memory devices, like in computers and any other device that basically works with memories, with storing memory of something, okay? So it's basically this capability of materials that are dielectrics that where I can change by putting or inserting an external electric field, I can align the dipoles with my external electric field. And if I revert, well, it will revert and I can basically complete a loop, a complete loop. That area within the loop will be basically equal or proportional to the energy per unit volume that is dissipated once a full cycle has been completed, right? And remember that for ferroelectricity, we have the Curie temperature, right? Once I reach the Curie temperature, well, I lose my properties of ferroelectricity. If I go back to low temperature, I will regain ferroelectricity, right? Curie temperatures range from negative minus 200 centigrades to 640 centigrades. It really depends on the material, right? So this is what happens, right? So I have domains, I have different domains in my material. And, you know, if I put an external electric field, they are all randomly oriented, right? If I put an external electric field, let's say in this direction, well, what will happen is that all those dipoles that I have there will start aligning in that direction. And that is the characteristic of a ferroelectric material. Okay? And remember, one material that exhibits this is barium titanate, right? If you remember from your ceramics course. And if I increase the temperature, I change the structure. Remember, my material becomes doesn't become symmetric anymore, and therefore that's why I lose the ferroelectricity. Okay. Piezoelectricity. Well, this is quite easy. So when if you apply pressure to a ferroelectric material, and you have a change in the magnitude of the polarization, it will result in a small voltage generated across the sample. Well, that is piezoelectricity. So basically, pressure being applied, change in the polarization, a small voltage is generated, piezoelectricity. Remember the best material for piezoelectricity, you might remember also that from ceramics, PZT. Piezoelectricity is basically utilizing all those devices that are designed to convert mechanical strain into electricity, right? Because I'm applying pressure and I'm generating a small voltage. Therefore, all those devices are transducers, like microphones, sonar detectors, phonograph pickups, and all that. That is the direct piezoelectric effect. I can also have, you can remember that from ceramics, the converse piezoelectric effect, when I apply an electric field and that electric field is producing a change in dimensions, and that will obviously can generate actually, or I need a 6, usually a 6, well, let's say in an order of magnitude of 10 to the negative 10 meters per volt. Okay, and remember the PZT materials are the best for that, and I can, or that is utilized, for example, in earphones, in inkjet printer heads, diesel fuel injectors, and obviously the most important application is quartz crystal resonators for clocks. Remember, clocks or radio frequencies, you have quartz for basically adjusting the distinct frequencies. Okay, so that's the most important use. That is the converse piezoelectric effect, when I apply an electric field and that produces a change in dimensions. Okay, but you already know that, it's quite easy. And then you can have electrostriction. That is basically the same as piezoelectricity, but it's just a quadratic relationship. So piezoelectricity obeys a linear relationship, while electrostriction basically obeys a quadratic relationship between the electric field and the mechanical strain, the mechanical deformation, right? But it's the same idea of generating a change in dimensions by an electric field. Okay, and then the last one, pyroelectricity, is just a temporary voltage is generated once the material is fully heated or cooled, right? Once I heat or cool the material and I see a temporary voltage that has been generated across the end of the material, well, that is called pyroelectricity. It's especially seen in this material, thallium, well, it's, how do you call that? Lithium thallium oxide. Yeah, and that is, yeah, well, pyroelectricity is really momentary. Okay, after some time, due to current leakage, that voltage disappears. And this is also important. All pyroelectric materials are piezoelectric, but not all piezoelectric materials are pyroelectrics. Okay, that's it for this module. And yeah, we finish in about 2 hours. Questions about anything, guys? I'm not sure. Let me see who's still connected. Is it only... Okay, 4 people. Any questions, guys? The slides are already uploaded, so you guys can check it. Oops, sorry. Okay, you guys can check these slides. The slides are already in Aula Virtual, and that's it. I guess I'll see you next Thursday for the exam, guys. Any questions? No?